Welcome to the rigid body equations of motion. Today we are going to discuss the heavy symmetrical top with one point fixed. The problem under study is that of a symmetrical body in a uniform gravitational field having a point on the symmetry axis fixed in space. And this is a good approximation for systems that in practice are used as navigational gyroscopes. And to set up the notations for this problem, I have a list here to go through. So in this particular case, we are going to denote the body set of axes by the directions x, y, z, since we will very commonly refer to these and less so to the laboratory frame. So these are the body set axes with z as the axis of symmetry, and then the Euler angle theta will give the inclination of the figure axis z from the laboratory vertical. Phi is going to be the azimuth about the vertical, and psi will be the rotation angle of the top about its symmetry axis. L is going to be the distance from the center of mass of the top to the fixed point along the symmetry axis, and then the derivatives of the angles have the following significance. Psi taken as a derivative with respect to time is the spin about the symmetry axis. Then the derivative of phi is the precession of the figure axis about the laboratory vertical, and the derivative of theta is the notation frequency of z, the figure axis relative to the laboratory vertical. Typical conditions that are valid in real-world applications are the ones where the spin velocity is much greater than the notation frequency, which in turn is much greater than the precession rate. Furthermore, we are considering that the since the body is symmetrical around the z-axis, the moment of inertia corresponding to the figure axis is different from the other two, which are equal. And if we use this condition in the Euler equations, we obtain explicitly the free equalities listed here. Now we are going to take under consideration the following set of initial conditions. Only the first component of the torque is non-vanishing, and only the third component of the angular velocity is non-vanishing. So the top is rotating only about its symmetry axis, and we have a torque applied in a direction that is perpendicular to it. So from these conditions, together with the Euler equations, it follows that the third component of the angular velocity is conserved, and at the same time the first component is not, due to the fact that n1 is different from 0, and consequently the second component of the angular velocity is also not constant in time. Now, from an observational standpoint, these dynamical statements are not overly obvious. The reason is because what we typically observe in the laboratory are the rates of change of the angular variables together with the corresponding angles. So these are observed in the laboratory frame, rather than observing, let's say, rates of change of the angular velocity and their corresponding angles in the body set of axes. So what this suggests is that Euler's equations might not be the most suitable dynamical equations for this problem, and that perhaps it would be more useful to recast the problem in a different language. The formulation in question is just the Lagrangian formulation of mechanics. Since a point is fixed, we only have to concern ourselves with rotational kinetic energy, which in the body set of axes will have the expression here. And if we write the components of the angular velocity explicitly in the body frame and plug them into the formula for the kinetic energy, we obtain the result given here. So this is the rotational kinetic energy up the top in terms of Euler angles and the principal moments of inertia. And for the potential energy, this is a very simple proof showing the result that we have already used in simple applications, namely the total potential energy is just a sum of such dot products over all the particles in the system involving the masses of the particles. But the sum that is implicit here simply amounts to the total mass of the body times the coordinates of the center of mass. So the total potential energy is just this dot product of the radius vector of the center of mass and involving the radius vector of the center of mass and the gravitational acceleration. And if we take into account this formula to get rid of the fact that the gravitational acceleration is pointing down, then the dot product itself has the value here, and as we've already established, the distance from the center of mass to the point of attachment, which is considered the origin of the coordinate system, is just L. So the total potential has the value here. Then the complete Lagrangian containing the rotational kinetic energy and the gravitational potential energy has the formula here. What we observe immediately is that this Lagrangian does not depend explicitly on phi and psi. So these are cyclic coordinates with conserved generalized momenta. As they are angular variables, this implies the conservation of the angular momentum components along the respective axes, namely conservation along the vertical axis for the angle phi and the figure axis of the body for the angle psi. Another way to see this comes from noticing that the torque of gravity is orientated along the line of nodes. Hence, there is no torque about the vertical or the figure axis, as they are both perpendicular to the line of nodes. In conclusion, the angular momentum along these axes is conserved. If we write them out explicitly, the formulas for the generalized momenta conjugate to psi and phi have these expressions, which are obtained in a very straightforward way just by taking the corresponding derivatives in the Lagrangian. And it is, since they are conserved quantities, it is customary to express them in terms of two constants A and B and the first principal moment of inertia. And these two results also follow quite simply from Euler's equations, namely the third equation is essentially identical with the statement of the conservation of the generalized momentum conjugate to the spin angle psi. And if we look at the set of Euler equations as a whole and we eliminate the components of the torque between them, you can show that what you obtain in a very straightforward manner is just the fact that the total time derivative of the momentum conjugate to the precession angle phi is 0. So in other words, you obtain the fact that this expression is constant. Furthermore, since the Lagrangian does not depend explicitly on time, this means that the total energy is conserved. So this quantity is as well constant throughout the motion. This is a set of first integrals to which we require an additional set of quadratures in order to solve the problem, and these quadratures follow immediately from the previous results. Namely, from equation 5.53 we can obtain immediately an equation for the time derivative of psi and as a function of the other two variables, namely the angle theta and the time derivative of phi, And then using this together with the result 554, we can obtain an equation involving just the time derivative of phi and the angle theta. So knowing theta as a function of time will automatically provide the angle phi as well. And then using this result together with the equation obtained above with 556, we can also express the time derivative of psi as a function of theta. So knowing the notation angle, we can, at a given moment in time, we can in principle calculate the precession and spin angles. Furthermore, from equation 553, we already know that the third component of the angular velocity is conserved, but we can give it a value in terms of this ratio of the moments of inertia and our constant A. So we can define an additional conserved quantity, which is just the total energy out of which we have subtracted the rotational energy for motion about the figure axis. And the advantage is that this new quantity, in light of previous results, depends solely on the angle theta and its derivative with respect to time. And in fact, it is reminiscent of the equivalent one-dimensional problem that we have studied in our discussions regarding the central force. Namely, we have a kinetic term and an effective potential, which depends only on the variable theta. So we have found four constants associated with the motion. The two generalized momenta conjugate to the angles psi and phi. This energy E prime, out of which we have removed the contribution of the spin rotational energy, and the maximum value of the potential, which is just m times j times L. And it is useful to cast these quantities in a, let's say, a normalized form in terms of the constants alpha, beta, a, and b, according to the formulas here. And what this allows us to do is to cast the equivalent one-dimensional problem in an even simpler form. And as stated, this can be treated quite similarly to the radial motion in the central force problem. Namely, once we have this result, we simply use this change of variables in order to obtain a differential equation of the form given here, and this can be integrated immediately to yield the following quadrature. So in principle, this result can be used to obtain phi and psi, but the problem is that the polynomial involved in this denominator is cubic, so it's trying to solve the problem this way leads to elliptic functions. Due to the inconvenience of working with elliptic functions, we need to find another way to understand the general characteristics of the motion of a heavy symmetrical top. And in order to do that, we need to discuss a bit the general characteristics of the constants and variables that are involved. So once again, let's begin by assuming that the fixed point is not the center of mass. Then if the top is spinning on a horizontal surface, both quantities alpha and beta that were previously defined are positive, while in the case of a top that is allowed to dip below the horizontal, beta remains positive, but alpha can have either sign. In the case of a gyroscope, in that particular situation, the fixed point is the center of mass, and in that case beta is equal with 0, while alpha is always equal or greater than 0. Furthermore, throughout this discussion we will mainly be interested in the cases where the spin kinetic energy is much larger than the rotational energy about the other axes. So the dominant component of the motion is the spin rotation, and the precession and nutation of the top act mainly as small perturbations to the overall spin motion. The result 562 prime, which we have just derived, can be recast in the form here. So this is just an identification of the right hand side of that equation with the function f of u, f of the variable u, which we will study a lot in our discussion of the motion. And so this is generally a cubic function in u, but for the particular case of the gyroscope, since beta is equal to 0, f of u will be a simple quadratic function. Furthermore, generally gyroscope applications use torque-free mountings that suppress precession and nutation, and overall this leads to a very trivial motion of the gyroscope. In the general case where we study the heavy symmetrical top, we will be concerned with those problems where beta has a positive value. Now, the roots of this f of u function furnish the angles at which the time derivative of theta changes sign. So these roots are the turning angles of the variable theta. And we have the following possibilities. Either we speak of a real root and two complex conjugate roots, or we speak of three real roots with one of them being a double root, or we have the case of three real and distinct roots. The nature of the roots is fixed by the relative signs and magnitudes of the parameters listed in the set of equations of 5.61. Furthermore, notice that the variable u is bounded between the values -1 and +1. We are interested in the case where u is positive, so that is a heavy top supported by a horizontal surface. When u is large, the dominant term in f of u is the cubic one. So as we are interested in the case where beta is positive, it follows that this expression will always be positive for large positive values of u. Furthermore, at the physical boundaries of this parameter, so when u is equal with plus or -1, f of u has the value here, so it is always a negative function at the boundaries, unless it happens that the points at which u is equal with plus or -1 are roots, and this situation corresponds to a vertical top. So the conclusion here is that there are two roots in the range bounded by -1 and +1, and the third root is located at u greater than 1. As mentioned, physical motion can occur only when the square of u is greater than 0 in the range bounded by -1 and +1, and thus the angle theta belongs in the range between 0 and pi. So for an actual top, there will be two roots, u1 and u2, in the range between -1 and +1. And the top moves in such a way that the cosine of theta is bounded between these two roots. The location of the roots, together with the behavior of the precession rate and spin rate for the angle theta between them, provides much qualitative information regarding the motion of the top. In graphical depictions, the figure axis of the top is drawn at its intersection with a unit sphere centered on the fixed point. This curve is known as the locus of the figure axis. The polar coordinates of a point on the locus are just the Euler angles phi and theta for the body system. The locus is bounded by two circles given by these two values, theta 1 and 2, in terms of the arc cosine of the two roots u1 and u2, and the time derivative of theta vanishes at both circles. The shape of the locus is largely determined by the root of this equation, so by the value u prime equals with b divided by a. Now, in the case in which this root is larger than u2, the time derivative of phi will have the same sign both at the angles theta 1 and theta 2. So the locus is tangent to the bounding circles in such a way so as to preserve the direction of the precession rate. So the angle phi precesses secularly in a given direction, and the top precesses about the vertical axis. However, this is not a case of torque-free precession due to the figure axis moving between the circles. In fact, we speak of nutation during precession. Specifically, if the ratio b over a is such that u prime is in the range between u1 and u2, then the figure axis draws loops as it moves from one bounding circle to another. The average precession rate will not necessarily vanish, so there remains a net precession. In the situation where this root is equal with either u1 or u2, both time derivatives for the nutation angle and the precession angle vanish at the bounding circles, leading to the locus curve forming cusps there. This corresponds to the following set of initial conditions. So at the initial moment, the nutation angle has a non-vanishing value, theta 0, while the corresponding time derivatives of theta and phi are both equal with 0. So it is implied that u0 being equal of this cosine is a root of the function f of u, and the following equality will hold. The important statement made by this relation is that the value u0, which is a root of f of u, also happens to be one of the bounding circles for the motion of the heavy top. Now, with these conditions, if we look at the energy of the system from which we have subtracted the spin motion, it follows that we notice that the kinetic term is always positive. So as the time derivatives of theta and phi begin to differ from 0, the conservation of energy will thus require that the potential energy diminishes, which further implies that the values of the angle theta must increase. In conclusion, the value of theta 0 is equal to theta 2 is the smallest possible value that this angle can acquire. After that, it always has to increase in order for the energy to be conserved. So when the top is released in this manner, the top always starts to fall and continues to do so until the angle theta 1 is reached, and all the while the top is precessing. The figure axis then rises again towards theta 2. For these same initial conditions, we can assume that this additional condition is valid. In this situation, so where the spin rotational energy is much larger than the kinetic energy, precession and nutation are effects of gravitational torques that perturb the rotation about the figure axis. This is the case of what is known as the fast top. For such a system, the extent of nutation is given by the difference between the two values of u1 and u0. So if we look at the initial value of the energy, which is just the initial potential value, so for vanishing precession and nutation rates, and by removing the spin rotation from the discussion. So for this initial condition, alpha, turns out that the constant alpha has this value in terms of beta and u0, and if we use this together with 565, we can factorize the function f of u as shown here. And then if we look at this additional function j of u, we would like to find its roots, which we've labeled by U1 and which will be given as the um, solutions of this quadratic equation. Now we can include two additional notations. We will denote the difference between U0 and U by x, and the total amplitude of nutation will be the difference between U0 and U1. So this is the difference of the values of the cosine of theta at the two bounding circles. So this is noted by x1. And putting these things together in 568, you can show quite simply that this equation reduces to the following quadratic equation x1 in terms of the coefficients p and q that are given here. And now, in the case of a fast stop, what condition 566 implies is that p is much larger than q due to this ratio. So a particular situation where this would not be true would be the case of a top shaped like a right narrow cylinder, as that would involve that the third principal moment of inertia is much smaller than the first one. In any case, if this holds, and then we can treat the result 569 to first order in q over p, and it follows that the only available root is x1, which is equal specifically with q over p. And then if we neglect the value of 2 times the cosine of theta 0 as compared to the ratio a squared over beta, which is going to be a very large number, it follows that x1, which is the extent of nutation, has the expression here. So notice that it goes down as 1 over the square of the third component of the angular velocity. So a top that spins faster will have a lower nutation. To find the frequency of nutation for the fast stop, we will approximate 1 minus u squared in equation 557 with the squared sine of theta 0, and this is due to the low amplitude of the motion. Then if we put 567 and 570 together, we can recast f of u in the form of this differential equation, and we can change the variable x to a new variable y, which is defined in this way, and its time derivative will be equal with the time derivative of x. And the reason we do this is because if we perform the change, then the differential equation acquires the form here. And if we take the derivative with respect to time again, it turns out that this is just the equation of a simple harmonic oscillator. So with the initial condition that the notation has 0 amplitude at the initial moment, the complete solution for the notation problem is the one given here, with the coefficient x1 given by equation 570. And then the angular frequency of nutation follows as the result here, so it's the ratio of the moments of inertia times the omega free component of the angular velocity, and we see that the angular frequency of nutation in fact increases with spin. Having solved the problem of nutation, we can look at the precession problem. So from the result 557, we can approximate the precession rate with the ratio here, and then we can use the results 570 and 571 to immediately find the precession rate as given here. So the rate of precession varies harmonically with time, having the same frequency as the nutation motion. And if we calculate its average over a period of the motion by the same formula that we have used several times before, we see that this it's trivial to show that this integral reduces to just to the period tau, so the average precession rate is given simply by the ratio of beta to the twice the value of a. So in terms of more physical quantities, the ratio here. So the average precession rate decreases as the spin increases. Putting everything together, we have developed a full picture of the fast top having zero initial velocity for the figure axis. So this discussion involves a top that initially only rotates about the figure axis without the axis itself having any sort of motion. So what happens is that upon release, the top falls under gravity. As it falls, the torque around the axis of fall causes the top to pick up a precession velocity directly proportional to the extent of the fall, which gets the figure axis moving sideways about the vertical. The initial fall results in a periodic nutation of the figure axis in addition to the precession. Nutation decreases quickly with increasing spin, but its frequency increases while the precession rate becomes slower. In practice, for a fast top, the nutation is damped by friction of the pivot and becomes unobservable. This makes the top appear to precess uniformly about the vertical. Klein and Sommerfeld call this pseudoregular precession. If nutation is entirely neglected, the top immediately precesses uniformly, a motion that is normal to the gravity that causes precession in the first place. This is a paradox which is resolved by pseudoregular precession. Precession builds continuously from rest without infinite acceleration, and the initial tendency of the top is always to fall under gravity. We can now look at a slightly more complicated problem. Namely, we would like to see what happens if at the initial moment, aside of the top spinning about its axis, it also has a non-vanishing value of the precession rate, and this value is considered very large compared to the net or average precession velocity, but at the same time it should be small relative to omega free, and consequently it's small relative to the spin velocity. Then from energy conservation we have the same cubic function f of u, but the constants alpha and b are slightly more complicated as they involve a term having this initial precession velocity included. And by inserting these in the function f of u, the calculations are simple but quite lengthy, and not quite, fairly lengthy, and what they lead to is the conclusion that f of u can be once again factorized in this form. So one of the roots is u0, and the other root is contained in the function j of u, which will have the slightly more complicated expression here, because it has to involve the values of the phi 0 as well. So there should be a 0 here, which is missing. And so if we want this function to vanish, we end up with the quadratic equation written here, or if you want to cast it in an equivalent form, you can write it in this way. And the reason why you would like to write it like this is because this is simply the quadratic equation that we had obtained earlier for the roots x1, but in terms of coefficients p and q that are once again involving these. So there's a 0 missing here as well, which are involving these values. And the ratio q over p, if you can calculate, it's approximately equal with this expression. The thing is, we will constantly be neglecting, so we are constantly considering that this quantity is small relative to omega free, and consequently it's small relative to A. So we get this first factor in the expression, and then for the second one we can just use a Taylor expansion to write it in this form, and thus the ratio Q over P is just approximately equal with the quantity here, and as this is a small number, to first order the value of x1, which is just the total amplitude of nutation, is given by the formula here. So it's very similar to the previous result, but it also involves this this additional term. And then the rest of the problem is solved in exactly the same way. So f of u can be approximated by this function, which is equal to the squared time derivative of the variable x, and by using the exact same trick of doing a change of variables, changing to the variable y with the exact same functional relation to x, we can once again find that the extent of nutation evolves in time according to this function, but with the coefficient x1 given by the value here. So then, since this is a low amplitude motion, we can once again approximate the sine of theta with its initial value, and using the variable x defined in this way, then the precession rate will be approximately equal to the quantity here, and the net precession velocity will have the exactly the same formula. So it's just beta divided by 2 times a over a whole period of the motion. Now, assuming that this net precession rate is much smaller than the initial value, then this set of equalities and approximations holds. So we can approximate x1 by this value. We can approximate the derivative of 5 with respect to time as this function, and we can approximate, and from the extent of nutation we can find the time derivative of theta to be equal with this quantity. And the reason why we want to do this is because if we write the components of the angular velocity in the body frame, and we apply all of these approximations, so in particular the simplest one for omega 3 is the approximation of this value being essentially given just by the time derivative of psi, then if we put these approximations in these expressions, it turns out that as a function of time, the 3 components of the angular velocity behave as shown here. So these should look quite familiar. What we are seeing is that the third component is constant, and that the perpendicular component to it precesses periodically in time. So what we have shown is that the motion of the axis of rotation about the symmetry axis, as seen in the case of a free body precession, just appears as the nutation of the top in the course of its forced precession. And this holds under the assumption of a fast top having a mean precessional frequency much smaller than the initial value. So what you see is that both results are simultaneously valid, and this is quite relevant in the discussion of the dynamics of the Earth. Whereas we have seen previously, on the one hand, we can discuss its free body precession in the form of the Chandler wobble, but as we will see in the future, there is also a forced component to this precession due to weak gravitational torques, which is known as the precession of the equinoxes. Another question worth considering regards finding the initial conditions that lead to true regular precession. So this would be a dynamical regime where the notation angle is rigorously fixed and its time derivative is always 0. So what these conditions lead to is the fact that the function f of u must have a double root at u0. So both the function and its derivative must vanish at this point. So explicitly, what the first condition implies essentially is putting result 562 prime together with the vanishing of the derivative of u, and this implies the relation here. And the second condition regarding the vanishing of the derivative corresponds to this result. And if we put these two together with the result 557, we obtain an equation, a quadratic equation for the precession rate in terms of the constant value of the angle theta and the beta constant of motion and the constant a. Now this result, together with with the set of constants given in the equation 561, leads to the equation for phi having this form, or alternative the form given here. And it is important to note that this result will follow directly from Euler's equations. So if we just write them explicitly, it's not incorrect to write them in this way, but obviously since this is equal with the I1, it should be I1 here. So if we write them in this form, and then we look at the components of the angular velocity in the body frame for this explicit condition of true regular precession, then with these quantities and by writing the torque down, of course the torque will just be given by this cross product, and it's easy to write it explicitly in this form and then transform it to laboratory coordinates, for example. So if we put all of these things together from the Euler equations, you will immediately find the exact same condition. Furthermore, the magnitude of the orbital angular momentum is invariant to an orthogonal transformation. So on the one hand, L squared must be the same whether we evaluate it in the body or in the laboratory set of axes. We know that the sum of squares of these two angular velocity components is equal with this value, and as we have seen in the previous discussion, the vertical component of the angular momentum in the laboratory frame is constant and is equal with this value. So if you put these things together, you can show that the sum of squares for the x and y components of the angular momentum in the laboratory frame, this sum depends only on the is overall a constant depending only on the cosine of the angle theta. So if the top recesses uniformly about the vertical, then so does its angular momentum vector, as is proven here, because this will be a constant as well. Alternatively, you can show that this follows immediately from by evaluating explicitly Newton's second law. In any case, the initial conditions for the motion of the heavy symmetrical top are given by this set of values, so the Euler angles and these two time derivatives, in either the time derivative of psi or the value of omega free at the t equals 0. As phi and psi are cyclic, their values are largely irrelevant, while for the others we can choose arbitrarily. However, restrictions come into play if we want the motion to consist in uniform precession without any form of notation. In that case, either form of equation 557 must be satisfied. And for a vanishing derivative of theta with respect to time, we can choose theta and omega free almost arbitrarily, but then the derivative of phi is going to be constrained. The term almost is implied due to the fact that equation 557 is quadratic and it requires the derivative of 5 with respect to time to be real. And so that will involve that this condition must hold. Then if theta 0 is greater than pi over 2, so if the center of mass is below the fixed point, any value of omega 3 will lead to a uniform precession according to this result. However, if theta 0 is smaller than pi over 2, then omega 3 must be larger than a critical value, which is given by the expression here. And similar constraints can follow from the alternative form 557 prime. The quadratic nature of equation 577 leads to two regimes in phi, which are known as the fast and slow precession. For finite values of the derivative of psi with respect to time, or alternatively of omega 3, the vanishing derivative of phi with respect to time is never a solution of equation 577. So the top must always be given an initial shove to start the motion, otherwise at best we obtain the regime of pseudoregular precession. In the slow case, so the one in which this inequality holds, then it follows immediately that the derivative of phi is approximately given by the ratio of beta to 2 times a. So the result here, which is the slow case. And this is just the average precession rate for a fast stop undergoing pseudoregular precession. What we mean by this is that for a slow precession there is little difference between starting with a small shove or no shove at all. And this is entirely equivalent to the statement that omega 3 is much greater than the critical value. For such large values of the spin, the fast precession is obtained when the derivative of phi is so large that the maximum value of the potential energy is small compared to the other terms in 577. And this leads to the fast precession regime, which, as you see in the expression here, is independent of gravitational torques, and thus it is related to the precession of a free body. A final interesting point of discussion is given by the situation where u being equal with 1 happens to be a root of f of u. And we are supposing furthermore that the figure axis is vertical at t equals 0, so then the constants b and a will be equal, as their values multiplied with I1 are just the constant angular momentum components about the vertical and figure axis, which are coincident in this case, since I1 will be the principal moment of inertia about the same axis. Then the total energy from which we subtract the rotational spin component is just the potential energy. So together with the definitions in the set of equations 561, it follows that alpha equals with beta, which leads to the following form of our function f of u. So we see here that u equals with 1 is a double root, and the third root is found by solving this equation, and is equal with the value here. In the case of a fast stop, a squared over beta will be much greater than 2. So in this case, this third root will be greater than 1. And then the only possible motion occurs when u itself is equal with 1. So the top simply spins about the vertical. Otherwise, if it happens that u3 is smaller than 1, the top will nutate between theta equals 0 and theta is equal with the value corresponding to u3. In the particular case in which a squared over beta is exactly equal with 2, we obtain the critical frequency omega prime squared equal with this ratio, which is identical with the result 579 for uniform precession at theta 0 equal 0. In practice, if a top spins vertically with a frequency greater than the critical value, it will maintain a steady state for a finite amount of time, and this is known as a sleeping top. What happens in reality is that as friction gradually slows it down and reduces its spin velocity under the critical value, the top begins to wobble with a larger and larger amplitude. Furthermore, friction is very relevant in another case, which is the system known as the tippy top, namely a top consisting of a body slightly larger than a hemisphere with a stem added on the flat surface. If rotating with the spherical side downward on a hard surface, the top will skid and nutate until it will turn upside down and sleep along the stem. The reversal of the angular momentum vector is the result of frictional torque occurring as the top skids on the spherical side. Now, practical applications of all of these concepts involve a large body of navigational technologies that are based on gyroscopes. A free-frame gyroscope is a symmetrical top rotated very rapidly by external means about the figure axis and mounted in gimbals so that the motion of the figure axis is unrestricted about three perpendicular spatial axes while the center of gravity remains stationary. The figure axis maintains the same direction in space no matter how the mounting is reorientated, which is a phenomenon known as gyroscopic inertia. Under suitable torques, a gyroscope will exhibit precession and nutation as discussed previously. However, the system is a fast top, so nutation is always of small amplitude and damped out by the method of mounting. The observed phenomenon then is mainly precession. Now, in the case of a gyroscope, the torque is given by the cross product here. And now if we consider that the spin angular momentum is parallel with the figure axis of the top, and that the precession vector is parallel with the vertical axis of the laboratory system, having a magnitude equal with the mean precession rate of equation 574, then the sense of magnitude of pseudoregular precession follow from the cross product here. So any torque about the fixed point or the center of mass can be cast in the form of a cross product between the radius of the radius vector of the center of mass and the force, as in the case of equation 5.81. So the average precession rate for a fast top can always be derived from equation 5.82, with the direction of f defining the precession axis. Applications in real world will generally involve equilibrium behavior and neglect transients in the motion. Free of any torques, a gyroscope spin axis will always preserve its original orientation relative to an inertial system. Angular rotation rates and applied torques can be determined from equation 5.82. This equation also shows that the precession rate is proportional to the torque, whereas in a non-spinning body it is the angular acceleration that is given by the torque. Once the torque is removed, a non-spinning body continues to move, while a gyroscope continues to spin without precessing. The gyrocompass is a bit more complicated due to, in that case, dealing with a gyroscope that is fixed in a non-inertial system while the Earth rotates underneath it. However, the basic principles of such a system can still be illustrated quite simply. To understand the principles behind the gyrocompass, we must first consider a more general problem. Namely, let a system of particles interact with a central potential in an inertial reference frame that happens to be coincident with a frame rotating with fixed angular velocity omega 0. Then the Lagrangian is just T minus V. The kinetic energy is given by the usual summation over the masses and product between masses and the squared velocities of the particles, and we can write the velocities down according to the motion of the rotating frame. So if we put all of these things together, then the expanded Lagrangian has, written with respect to the rotating frame, has 4 terms. The first one is just the kinetic energy of the moving particles, but with respect to their velocities in the rotating frame. The second term happens to be just the dot product between omega 0 and the angular momentum written in the rotating frame, so this is just the Coriolis term, while the third term is a scalar resulting from the contraction of the inertia tensor written in the rotating frame. So the inertia tensor of the system contracted with twice with omega 0. So this is just the rotational kinetic energy, which is seen in the rotating frame by the fact that the system as a whole appears to be rotating. And of course the potential energy is invariant, since it depends only on the relative distances between the particles, and these are unaffected by such transformation. Then, having this result, we can consider a system of particles that is in fact a fast symmetrical top, with its fixed point being the center of mass and the potential being equal to 0. We are assuming further that omega 0 is in the y prime z prime plane, while the figure axis of the top is fixed in the x prime z prime plane, such that phi is always equal to pi over 2. So essentially what we're doing here is we're saying that z prime is the geographical north, and then omega 0 is just the rotation axis of the prime frame, which is, in our case, it simulates the rotation of the Earth. So then the diagonal form of the inertia tensor, which is valid in the body frame of our fast symmetrical top, can be obtained by a similarity transformation from the inertia tensor as seen in the frame of reference attached to the rotating Earth. So then if we invert this equation, we obtain the primed form of the inertia tensor in terms of the diagonal form, and then the components of the angular velocity of the body as seen in the rotating frame of the Earth will follow from an orthogonal transformation of the angular velocity as seen in the body frame. So this is done by applying the transpose of the transformation matrix A, and of course with phi being fixed in the body frame, the angular velocity vector will have these 3 components. And then of course we have a kinetic energy for the rotation of the body as seen in the Earth frame. So this is the proper rotation of the body as seen in the Earth frame, which is this contraction, and the angular momentum is of course given by this contraction. So then if we take all of these things together and work out the transformations, it might seem maybe a bit compelling, but it is in fact quite simple once you apply all of these definitions. So because since these are orthogonal transformations, a lot of these products will reduce to the identity matrix and so on, and things are quite simple since we also know that this angle is fixed. And what we obtain is that the kinetic energy of our top as seen in the Earth frame should have this value. Then the Coriolis term is given by this expression, where these two components, y prime and z prime of the vector omega 0, are just the components along the y prime and z prime axes, and then the rotational kinetic energy, which is the term here, again through a very basic calculation, has the expression here. Now, the idea is that since the top is fast, its spin frequency is much faster than omega 0. So in that case, we simply neglect this rotational term, and then for the remaining Lagrangian, if we look at the equation for the variable theta, it simply reads as shown here. So this is just the pendulum equation, and then for small oscillations it behaves like the equation of a harmonic oscillator, having the frequency capital omega shown here. So in other words, what happens is that in this simple example, if our spinning top ends up oscillating around the direction of the geographical north, and this this example would illustrate the basic principle of a geocompass, of a gyrocompass. The full treatment is a bit more sophisticated, but ultimately, so it involves more transformations and calculations for more general conditions for the motion, but ultimately it still reduces to it can reduce to the result that we have presented here. So in summary, we have discussed the dynamics of the heavy symmetrical top with a fixed point in great detail for a variety of initial conditions. We have studied the following particular cases, namely the one of pseudoregular precession, true regular precession, and the case of the sleeping top. We have summarized the basic principles behind the technological applications of the gyroscope, and we have illustrated the working principle of the gyrocompass. And in the following, we will discuss one of the most important applications of this chapter, which is related to the dynamics of the Earth and the precession of the equinoxes. All that being said, I want to thank you very much for watching. I hope you found the discussion worth your time, and I will catch you later. Goodbye.